So to recap where we left off, in the last lecture we had started into the second unit of study, matter and energy, and we had essentially defined a lot of terms. It's a rather big departure from what we were doing in the first unit of study, which was a lot of dimensional analysis, a lot of calculation. This sort of put us into a different realm, that of defining terms. We looked at since we're looking at matter and energy, we started with matter, this concept of matter as well as its properties. We determined that a sample of matter can either be a pure substance or a mixture. So in those two ways, we can break them down further with respect to a pure substance. A pure substance is either an element or a compound, which we defined before. Also, with respect to pure substances, we looked at different properties, chemical versus physical properties of matter, and along with those properties, the concept of changes in pure substances, chemical versus physical changes in a sample of matter. To round things off, we began our discussion about mixtures, which is essentially two or more pure substances together in a mixture, fairly obvious. We defined a homogeneous mixture as different from a heterogeneous mixture, and we were able to leverage differences in physical properties of mixtures in order to separate them, and that is where we left off last time. So let's continue our conversation about matter, and we'll specifically try and bring our discussion of matter into a chemical realm. How do we express matter with respect to chemistry? And that's virtually always by looking at what's called a chemical equation of reaction. A chemical equation of reaction in its most base forms. We have on the left-hand side, we have a series of reactants. On the right-hand side, we have a series of products. And there's always an arrow pointed from left to right describing that, or describing the flow of that reaction. So if we're to look at this concept of matter under the microscope, if you will, of a chemical equation of reaction, let's look at some examples. Now, again, I'm going to be taking some license here. If we look at some of these example chemical equations of reaction, there's a lot that we still have to specifically define. You know, what exactly are these letters abbreviating, and what are these, for instance, these subscript numbers? Now, many of us have had chemistry before, and we understand what these are, but because this is an all-inclusive course, we're eventually going to express what they mean. For now, I just ask that you give me a little license to put some of these up here in the absence of their description, just so we can begin to set our foundation. So having said that, here are two representative examples of chemical equations of reaction. We have the reactants in both cases over on the left-hand side. There's a left to right arrow, and the products over on the right-hand side. So with respect to chemical equations of reactions, since there are two things in the universe, that would be matter and energy, almost always we only express matter in a chemical equation of reaction. This is considered the matter component of the reaction, is always shown in a chemical equation of reaction, always, to the exclusion of the energy component of a reaction, which virtually always is always there. It's just never expressed. So let's look at these two examples of a chemical equation of reaction in which the energy component would be shown. We're just going to put these in there. Normally we would not see this, but it's almost always there, hiding behind the scenes. Now, when I talk about energy in a chemical reaction, the type of energy is almost always heat energy. we're going to find that there are many different types of energy. There's the energy of motion, that's kinetic energy. There's visible light energy. There is heat energy. But almost always when we're looking at this idea of energy in chemical reactions, almost always we're talking about with respect to heat. Now, if we look at these, if we look at the top reaction, we have this energy component is over on the right-hand side. It is part of the product profile. That means going from reactants to products, we're going to have a release of energy on the product side. That energy, heat, that energy must be given off as heat. The energy is being released in this reaction, so we call this an exothermic reaction. Energy is being released. Now, alternatively, we can have an energy component of a reaction, heat energy, on the left-hand side. So here over here, we see energy on the left-hand side. That means that in order for reactants to go to products in this chemical reaction, we have to have heat energy being put into it. So it uses energy to go from reactants to products. This is known as an endothermic reaction. If we had to put these all into a nutshell, we could say that an exothermic reaction, the one on top, is one which releases heat energy. So if I had a chemical reaction going, which I knew was exothermic, I would, as the reaction progressed, I would feel the reaction vessel begin to heat up a little bit. That's getting hot, so that must be an exothermic reaction. Alternatively, if I had an endothermic reaction, one that requires energy, if I felt the temperature of the reaction vessel with my hands or something like that, we would notice that the reaction would be cooling down perhaps. So that would be indicative of an endothermic reaction. We are teaching at the level here where we're not, I would have to tell you whether a chemical reaction was exothermic or endothermic. In the absence of other mitigating factors where we could perhaps predict that, almost always I would have to express to you that this particular reaction is exothermic, this particular reaction is endothermic. So let's look at both the matter and the energy component of a chemical reaction with a couple of laws we're going to put in place. The first law of a chemical reaction is the law of conservation of mass, which states that in a chemical reaction, mass is conserved, meaning that the matter in it is conserved. It's neither created nor destroyed. With respect to a chemical equation of reaction, there better be the same amount of matter on one side of the reaction that there is on the other side of the reaction. There's two ways to express this. And if we look at a representative chemical equation of reaction here, this is a much more complex one than we looked at before, but don't let that sway you. The first way to look at the law of conservation of mass, here we have a representative chemical reaction, and here are our reactants, here are our products, essentially we have to be able to count. There will be the same number and types of atoms on both sides of the chemical equation. Now, the letter C in this case, as we'll eventually know, means the element carbon. The letter O is oxygen. The letter H is hydrogen. And these subscript numbers that we see here on both sides represent the numbers of them in each chemical formula. So thus, if we were to go through this particular chemical equation of reaction, we would be able to count the number of carbons, hydrogen, and oxygen atoms in there. And this was the number that we would come up with. 6 carbons, 18 oxygens, 12 hydrogens. Well, if we look over on the other side of the chemical equation of reaction and add up all of those carbon atoms, hydrogen atoms, and oxygen atoms, it better be the same, or it does not adhere to the law of conservation of mass and thus is not a correct representation of the reaction. So it's one way of looking at the law of conservation of mass would be essentially counting atoms. Do they add up on both sides? Another way of describing or expressing the law of conservation of mass would be with respect to masses of reactants versus products. So here we have a chemical equation of reaction written differently. I've written this such that I've spelled out the actual reactants and the products. So this isn't how you'd normally see this, but it's written in problem form. Butane here over on the left-hand side, this is what its chemical formula would be. So if we just had those chemical formulas in there for reactants and products, there is oxygen, carbon dioxide, and water, then this would be a bona fide chemical equation of reaction. However, it's written in the form of a question. Here we have masses, and we're not counting particular atoms, but we're given masses. 40 grams of butane as a starting material. Here over on the product side are a mass of carbon dioxide and a mass of water. And really the question is, if we have these masses going on, how many grams of oxygen are we going to require theoretically? And since the law of conservation of mass states that matter is neither created or destroyed, the total mass on one side must equal the total mass on the other, reactants to products. So this becomes set up in an elementary fashion, really, that we have, we just do some simple algebra. Here's the mass of the reactants with X as the mass of oxygen. Here's the mass of products, and we can very easily solve for the mass of oxygen. This comes out to be 15 grams. So moving over to the energy component of a chemical equation of reaction, and remember the energy component is almost never shown or expressed in a standard chemical equation, but it's always there, hiding in the background. So thus we have to have a similar law, which governs the energy flow in a chemical equation of reaction. And this is called the law of conservation of energy. The law of conservation of energy states that in a chemical reaction, energy is always conserved. It is never created or destroyed, very much like our law of conservation of mass, where mass is neither created or destroyed. Now, one difference here is that energy lost in one form can be gained as energy in another form. We had said before that there are many different types of energy, for instance, heat energy, electrical energy, light energy, energy of motion, that's kinetic energy, but it can always be transposed from one form into another, and looking at the total energy on one side of a chemical equation of reaction, it must equal the energy flowed on the other side of the chemical equation of reaction. So here is a representative chemical equation, and if we look closely, we see that this is something we've seen before. Up on top here we have 2 molecules of water goes to 2 molecules of hydrogen and 1 of oxygen. That's a chemical equation of reaction, and we find that we have an energy component sort of put in here. And this energy component is on the reactants side. So that means it must be it must be an endothermic reaction. This reaction requires energy in order to progress. Now we're going to find that any chemical equation written as in a form of a reaction is in essence and in theory reversible. We can take what once was the products and make them reactants. Whatever the reactant profile was, and make them products with that same left to right arrow that we've seen before. Now notice in this case that the energy which once was in the reactant side is now on the product side. And if we measured the amount of energy of these amounts of energy, they would be equal, exactly equal. They have to be due to the law of conservation of mass. Looking at this specific reaction, now let's look at the one on top. In which we have water being converted into its constituent elements, hydrogen and oxygen. This is actually a classic reaction that many of us have done before. If we take a sample of water, which we see here, and we run a low electrical current through it under specific conditions, it will cleave those water molecules, which are made of hydrogen and oxygen, into a sample of oxygen gas and a sample of hydrogen gas. This is typically carried out over a period of an hour or two, in which our sample of water then collects appreciable amounts of oxygen gas and hydrogen gas. Over the entire time, we have this slow flow of electrical energy. So that's the energy component on this side. We have a slow flow over time of electrical energy. Well, let's look now at the reverse reaction down here, in which we have, if we just turn this around, we would have our hydrogen and oxygen gases going back to water. But in so doing, we would release energy, the same amount of energy that took to go into carrying out the cleaving of this water sample into its constituent elements. Well, this is also a classic sort of reaction in which we take a mixture of hydrogen and oxygen, say in a balloon, which we see over here on the left, and we put a little spark to it to start the reaction going. And what happens is, and you may have seen this in videos or in reactions and classes you may have had in high school or something like that, is a very fast, explosive reaction, very explosive, very violent. Now, both of these energies are very different, but they are equal. The very slow flow of electrical energy over a period of an hour or two going into this reaction in this direction, that entire amount of energy is released instantly in the reverse reaction. So that very violent explosion that we see over here, if we were to measure the entire amount of energy, heat energy, would exactly equal the slow flow of electrical energy which went into its making. So let's look at the type of energy which we encounter when we consider specific reactants or specific products. There is a type of energy known as potential energy, which is sort of an ethereal term which is difficult to comprehend, that of potential energy. We could think of a large boulder perched on a hill, which seems like a very serene sort of atmosphere, but if that boulder starts to go down the hill, it starts to pick up kinetic energy, and there's a lot of energy there. The faster that boulder goes, and it can be very destructive at the bottom if that boulder were to crash into a house. Where did that energy come from, that energy of motion on the boulder? Well, that would be a type of potential energy known as gravitational potential energy, which you couldn't see, but it was contained in its potential perched at the top of the hill. A similar type of potential energy is manifest in the form of chemical potential energy. Chemical potential energy, we can't see it, we cannot measure it, but it is there and it's stored within chemical systems, specifically within the chemical bond structure within a series of reactants or a series of products. There's energy stored within that bond structure. Now, going from reactants to products in a chemical reaction, we break chemical bonds and we form chemical bonds. We call this a reshuffling, if you will, a reshuffling of chemical bonds in converting from reactants to products. Now, it almost always results in an energy imbalance. That's a potential energy imbalance, because the energy contained within the bond structure of the reactants is different than the energy contained within the bond structure of the products. This is invisible energy, if you will, potential energy, but it's different. and it almost always results in an imbalance. There's almost never exactly the same chemical potential energy in a series of reactants than there is in the products. And that energy has to be released somehow, or it has to be expressed somehow, going from reactants to products. Now, the way we typically look at this is through it's a two-dimensional scape known as a reaction coordinate. Reaction coordinate, where if we look at the structure over here on the left, on the y-axis we have an energy axis. It's an arbitrary energy axis. The higher we go is the higher potential energy contained within the bonds, the bond structure of reactants or products. The lower we go down here is a lower arbitrary amount of energy. So that's on the y-axis. On the x-axis, in this direction, we have what would be considered the progress of reaction. The progress going from reactants, if we shift to the right, towards products. So reactants to products, that conversion or that movement is on the x-axis. Notice what happens here, and I'm going to spell this out in as an exothermic reaction. How could we express an exothermic reaction? Well, it would be one in which the internal energy or the potential energy of the reactants is greater than that of the products. It just is. And once we get finished reshuffling those chemical bonds, we have extra energy, which must be released. An exothermic reaction. It must be released almost always in the form of heat energy. Almost always in that particular form. So again, our exothermic reaction, as it progresses, we could perhaps feel that reaction vessel heating up a little bit. That is because of this excess energy that must be released to the surroundings. It has to be released. Now, if we look over on the right-hand side, we have a different sort of coordinate where, again, we do have that energy axis, arbitrary energy axis on the y-axis, and on the x-axis, we have our progress of the reaction. So notice in this case, we have the stored potential energy in the reactants is less than that stored chemical energy within the bonds of the products. So the products is greater. So going from reactants to products, we must, in order to equal out the amount of energy, we must have a certain amount of energy absorbed by that system going from reactants to products. This was, by definition, our endothermic reaction, essentially the opposite of an exothermic reaction. Now, what is this amount of energy? So going from reactants to products here, what is this exact amount? Again, we are in the business in this class, we're looking at it at a level where we will not be calculating the specific amount of energy because a lot of different considerations have to go into that. Again, I would also, in the absence of information that might clue you in a little more, you would not know, or I would have to tell you whether a reaction happened to be exothermic or endothermic. But my point here is that this is what the reaction coordinate would look like for an exothermic reaction. This is what the reaction coordinate would look like for an endothermic reaction. So if we compare the total potential energy in between the reactants and the products, just to summarize, here we have, if we have greater potential energy in reactants, lower potential energy in products, that is an exothermic reaction. If that greater potential energy happens to be in the product profile, that is an endothermic reaction. So we've talked about the idea that energy can be in different forms: heat energy, electrical energy, potential energy, and that sort of thing. However, if we're going to be talking about energy, we have to define a unit of measure for energy, whether it is in the form of heat, whether it is in the form of electricity, and that sort of thing. We have to describe a unit of measure. Before I get into that, I do want to express, and when we're talking about energy, especially in a chemical reaction going from reactant to product, we're talking about energy flow. Whether that flow is positive or negative, as we saw in the previous slide, signifying an exothermic or an endothermic reaction, it is important to understand that energy in itself is immeasurable. Meaning we cannot directly measure energy. So the units of measure that we're going to be talking about in energy, to define energy, we cannot directly measure. We can infer them, and indeed we'll look at some equations which will express or allow us to infer the amount of energy flow going from reactants to products or in any one system into another. But it is, and I'm going to be using this term a lot in this course, it is considered immeasurable directly, but inferable. Having said that, let's take a look at our most standard units of measure for energy over here in this table right here. Now, I'll start. We have three essential units of measure down here, which we're going to be working with. And I'll start with the calorie. The calorie with a little c, as we see here, given a representative CAL. And we have a number over here as well, 1.00, exactly 1. And 1 what? What exactly are we talking about here? Somebody originally had to set up a yardstick. 1 calorie equals what amount of energy having to flow from one part of a system into the other. And the yardstick in this case would be the amount of energy, in this case it would have to be heat energy, or we would consider it as heat energy, the amount of energy required to raise the temperature of 1 gram of water, has to be water, by 1 degree Celsius. So 1 calorie is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. Pretty straightforward. So that was the original type of energy unit, if you will, and it held sway for a while. Nowadays, however, it is not considered a metric form of energy. A calorie as a unit of measure does not play well with other units, so that we had to come up with a different term. Before we get into that, I do want to show you that there are 2 types of calories. Here was our original calorie that we expressed with a lowercase c on calorie, but here now is another calorie with an uppercase c. That is also known as a kilocalorie because it is 1,000 regular old calories, if you will. So again, with the prefix kilo on there, it means times 1,000. Interestingly, this calorie with an uppercase c on it is known as the nutritional calorie. So when we're looking at the sidebar of a box of Cheerios or something and want to know how many calories are in it, it is the nutritional calorie which we're talking about, and not the smaller calorie, if you will. So the unit of measure that we will be working with using SI units is actually known as the joule. The joule, uppercase J being its representation. And as we can see by the difference in that in the calorie compared with the calorie, we can see that the joule is a smaller unit of measure. It just is. 4.18 joules equals 1 calorie. We could come up with a per expression for that because it's staring us right in the face. So when we talk about the joule, it takes 4.18 joules to raise the temperature of 1 gram of water by 1 degree Celsius. And that's the one we're going to be looking at most of the time, is the joule, because as we're going to see, it plays much better, much more nicely with other SI units of measure, like units of mass in grams, and so on and so forth. So that is the unit of measure that we're going to be working with most often. So we had already established that units of energy are immeasurable. We cannot directly measure them. The amount of energy which flows in a system can only be inferred. And as we will see, we will arrive at that term of energy mathematically. We'll be doing some calculations to achieve that. When we're talking about heat energy and heat energy flow either into or out of a system, going from the beginning to the end of the process, if heat is flowing in, the temperature of the sample of whatever that system is must go up. If heat is flowing out of that sample, the temperature must go down. Now, temperature is directly measurable, whereas energy is not directly measurable. How we're going to find that if we are able to measure temperature, a temperature change going from a beginning to an end point, we will be able to mathematically calculate the number of joules of energy which flowed in that process. So it is very important here that we be able to define temperature. Now, this temperature, we're sort of used to looking outside at the thermometer and saying, okay, it's it's this warm out or it's this cold out or whatever. Typically, looking at this from a physical standpoint, temperature by definition is the measure of the random kinetic motion of particles in a sample. Remember, getting back to our particulate view of matter, all particles of matter have movement. Whether it is the random movement of gases or liquids or the vibrational movement of the particles of a solid, it's all about movement. Now, essentially, with respect to temperature, from a particulate standpoint, the hotter the substance, the faster the movement of its particles, the greater the movement of its particles. And of course, the opposite stands true as well. The cooler the substance, well, its particles movement slows down. So, we can look at a picture here going from perhaps a cooler state to where we have an influx of heat energy to a warmer state. We can see that the particles of this substance, showing those little lines around them, are moving faster as we go from cold to hot. So the idea of measuring temperature itself sets itself up to look at the three different temperature scales. There's three different ways of expressing temperature. Just like we looked at different units of measure for expressing energy, some are more colloquial, but some are more amenable to working in the metric system or the SI system. So as we can see over in the bottom left here, there's three units of measure that we're going to be talking about with respect to temperature: the Fahrenheit scale, the Celsius scale, and the Kelvin scale. And we'll compare these one to one, differently between these three. I would like to look at some distances or some differences between the Fahrenheit and the Celsius scales. Now, in general, much of this is based upon the freezing point and the boiling point of water. Because water is a very ubiquitous substance. These two physical properties figure prominently into the different scales. So in Fahrenheit, water freezes at 32 degrees Fahrenheit and water boils at 212 degrees Fahrenheit. That's a 180 degree Fahrenheit degree difference. Whereas now on the Celsius scale, water freezes at 0 degrees Celsius and water boils at 100 degrees Celsius, giving us 100 degrees between the boiling of water and the freezing of water. So the Fahrenheit and the Celsius scales have a different size of the degree, and we have a different 0 point, if you will. So the Fahrenheit is a smaller degree, and the Celsius is a larger degree. Moving along, if we were to look more carefully at Celsius, it seems to be sort of fit into the program a little better, if you will. Whereas the freezing point and the boiling point of Fahrenheit seem to be sort of arbitrary and random, 32 degrees Fahrenheit to 212 degrees Fahrenheit. The Celsius pegs water freezing at its 0 point, and water boiling at its as a factor of 100, or within the scale of tens, if you will. So it fits a little bit more nicely. In fact, the Celsius scale is the one that's used most often in calculations based upon the international system of units, whereas the Fahrenheit scale has sort of fallen out of vogue. It's sort of like looking at the calorie as a unit of energy, as opposed to the more in vogue joule as a unit of energy. Now let's look a little more closely at the relationship between the Celsius scale and the Kelvin scale, because we're trying to juggle three balls at once here. Now notice that the size of the degree on Celsius and Kelvin are the same. Between the freezing and boiling of water in both Celsius and Kelvin is 100. 100 Celsius degrees is 100 kelvins. Now notice we don't say Kelvin degrees for whatever reason. They're just considered kelvins. A little housekeeping there. But the size of the degree is the same. The difference is their shift in 0 point. The 0 point for Kelvin is at minus 273 degrees Celsius, also known on the Kelvin scale, 0 kelvins, as absolute zero. Absolute zero. Now, where Kelvin comes into importance is with respect to movement of particles. As we decrease in temperature on the Kelvin scale, there is essentially, at least for our purposes in this class, no upper limit on temperature. If you took a physics class, you'd find that there technically is an upper limit, but for us there's no upper limit. However, there is a lower limit to temperature below which cannot exist in our reality. And that would be at minus 273 degrees Celsius, also known as 0 kelvins, absolute zero. Remember, as we decrease in temperature of a sample, the particles' motion slows down more and more as we approach absolute zero. And if we were to attain absolute zero, that is where all particle motion stops. And that is a physical impossibility. Thus, we've never been able to achieve absolute zero of a sample. We've become very close, perhaps a few hundredths of a degree above absolute zero, but it is an asymptotic scale, meaning we can approach it very, very close in many cases, but we can never attain it. Because the Kelvin scale, the size of the degree, is the same as Celsius, sometimes Celsius scales and Kelvin scales are interchangeable. Sometimes we'll encounter examples of this when we talk about the gaseous state, looking at some calculations in there where we have to use the Kelvin scale exclusively. But for the most part, when we're working with a temperature, Celsius is the one that is normally used. Now we see these differences between the three temperature scales. There are quite simple permutations and calculations we can use to convert one into the other. Now, going from the Celsius to Kelvin scale and vice versa, since it has the same size of the degree, it is a linear difference. And if we look at that difference, if we wanted to convert, say, from Celsius to kelvins, we would take whatever the temperature is in Celsius and add 273, and that would be the conversion between kelvins and Celsius. Very, very straightforward. When we're talking about Fahrenheit to Celsius, they have a different 0 point, but also a different size of the degree. Then we get a little bit more complex. and if we wanted to convert from Fahrenheit to Celsius, we put the Fahrenheit temperature within this calculation and subtract 32 divided by 1.8, and that would give us the degrees Celsius calculation. This leads us into a somewhat circular discussion. When we were talking about energy flow, we made a definition with respect to our energy units of measure that it takes 4.18 or so joules to raise the temperature of 1 gram of water by 1 degree Celsius. We're going to find that, taken in a larger sense, water has a specific capacity to hold heat or to absorb or to release heat, and based upon its fluctuation in temperature in doing so. So we're going to expand this argument from just water to all substances and define a physical property known as heat capacity. Heat capacity. It's also referred to as specific heat. It is almost always specific to a certain substance. Thus, it is a defining characteristic, perhaps, a physical property based upon what that pure substance is. And let's look at the definition now of heat capacity. And you'll find this very, very similar to something we've looked at before. It's the amount of thermal energy, look at this, in joules, okay, required to change the temperature, of 1 gram of the substance by 1 degree Celsius. That's very similar to what we looked at before. And as we said, the heat capacity is a defining characteristic, a defining physical property of a substance, different value for most substances. Now, let's look now at different different heat capacities for some common substances. The first one I would bring your attention to would be down on the bottom here, water. 4.18. They put a 4 after it too because they went to one further decimal point. But that number is something that we've seen before, 4.18. Remember, the definition of a joule was the amount of heat energy in joules, 4.18 joules, to take water from 1 gram of water up by 1 degree Celsius. So that was the 4.18 joules per 1 gram per 1 degree Celsius was the heat capacity of water. Whereas we compare this to other substances, ethanol, which is a liquid in its at atmospheric temperature or pressure and ambient temperature, that's different. For ethanol, that same gram of ethanol takes about half of the amount of heat to raise that by 1 degree Celsius. If we look at some common metals, again, solid at room temperature, we see a very, very small amount of energy required to take 1 gram of them up by 1 degree Celsius. Very, very small amount compared to that of water. In fact, water has probably one of the highest heat capacities known, and much higher than many other pure substances, which is one reason why it is used as a primary component in, for instance, radiator fluid. It has the capacity to absorb a lot of heat from your engine with a relatively small increase in temperature. So it has a higher capacity to absorb the heat, something very necessary. Now, if we look at our units of measure for heat capacity, it is in sort of really a jigsaw puzzle of units of measure, but it makes sense. Joules per gram per degree Celsius. That's what we're looking at. The number of joules per gram per degree Celsius of that substance. So it really does make sense. So we'll see that those units of measure actually work out if we were to use the heat capacity of a substance in a calculation, and we indeed will do that. Why would we do that? Well, what if we were looking to calculate the heat capacity, or I'm sorry, the heat which flows in a system, the heat which flows, that is immeasurable. We don't have a jouleometer or something like that, which we can put into a system and out pops the number of joules of heat that are flowing. That is impossible. However, heat in joules can be inferred. It can be inferred because the heat in joules is proportional to the temperature change going from the beginning of a process to the end of a process. So here's an equation which puts that together. Let me introduce that. Typically, heat in joules is given or represented as lowercase q. Why is that? We don't need to know. It's just that when you see Q, we're talking about heat in joules, equals the mass of a sample, so that's the system we're working with, in grams. Again, there's that grams term up there. Mass in grams times its heat capacity, which is, for a pure substance, is a known defining physical property, given as lowercase c here, heat capacity, times delta T. Delta, the Greek letter delta, signifies the change. It's not asking for a temperature, it's asking for a temperature change going from an initial set of conditions to a final set of conditions. So if our initial set of conditions was 15 degrees Celsius and our final set of conditions, the temperature was 20 degrees Celsius, that delta T would be 20 minus 15 would be 5 degrees Celsius. So that, notice we have in this equation now an equation of four unknowns, or rather four variables, and example problems in which we're asked to calculate this, that, or the other thing could come in the flavor of calculate heat, given these three others, if you will, or calculate mass, given heat capacity, and temperature. So always in these cases, in one form or another, you'll be in a sort of a heat capacity problem, you'll be given three of the four variables and be asked to calculate that fourth. So let's look at some examples. So here's a classic one, and again, it could be any number of the variables we're asking to solve for, and that is one of the tasks we're asked to do, or asked to discern when looking at a word problem. If 57 joules of heat are added to a 17.1 gram aluminum can, which essentially means a 17.1 gram sample of aluminum, what is its temperature change? So first of all, if we look at this, it already appears like I've lied to you, because we have 57 joules of heat are dialed into this aluminum can. If heat is unknown, if it is immeasurable, we're not able to measure the amount of heat flows, how do we know we're going to be inputting 57 joules of heat into the can? I will ask you to suspend your disbelief here, because we're just looking at an example in which to solve a problem. But looking at this, we can immediately see that, oh, okay, we're talking about joules of heat. We have a mass, temperature change. That was delta T, wasn't it? Putting on our sleuth's hat, we would be drawn to the fact that we are going to be using this classic equation, Q equals mc delta T. And we're ultimately going to be solving for delta T, because it's asking what is its chemical change. Now this is an equation. I should mention we have an equation here. It's not a dimensional analysis where we have what do we have, what do we want, and how are we going to get there by multiplying through. This is just a regular plug and chug action into an equation. So we're basically going to, if we're looking for the change in temperature, delta T, that means that the three other terms, heat capacity, mass, and heat, must be either made available in the question, or they must be something that we can look up. And indeed they are. So if we are to, let's see, in the question itself, it gives 57 joules as Q. So we put that in there. The mass of the can is 17.1 grams. The heat capacity of what? Well, aluminum. That is, we can go back to that table and find that heat capacity of aluminum as a physical property of aluminum and plug that in. And then we are solving for delta T. And at this point, it simply becomes algebraic. We get delta T all by itself on one side of the equation, and we multiply and divide through to get our answer. Notice 3.7 degrees Celsius is not what comes out of our calculator. However, we need to round that number to two significant figures because the least accurate term on here is two significant figures. And since we're multiplying or dividing, we would round whatever came out of our calculator to this 3.7 degrees Celsius final answer. Let's look at another one. As we see in the word problem up top, 32.5 grams of an unknown metal. An unknown metal. Okay, let's keep that in mind. At a temperature, initial temperature of 25.5 degrees Celsius, absorbs 42.7 joules of heat. Well, again, how do we dial in exactly 42.7 joules of heat since it's immeasurable? Bear with me. We are going to be suspending disbelief in here. We're just plugging and chugging into an equation, and off we go. Raising the temperature of the metal to 28.9 degrees Celsius. So now we have two different temperatures. Remember, we have a delta T term in here where we would just subtract one temperature from the other to get that. So that is something that is hiding in plain sight in this word problem. The big question here is, what is the identity of the unknown metal, since it is, as said before, unknown? Well, how do we go about identifying substances? Much of the time we can utilize, we can compare them to their physical properties. And if we can measure a physical property, much of the time we can say, oh, this physical property states that it is this particular substance as opposed to that one, like we did with density before in the last unit of study. But looking at this more broadly, we would have to recognize, like, okay, we're going a temperature change, we're dealing with joules of heat. Again, we're going to be looking at that classic Q equals mc delta T. And if we look at this now, what is the unknown that we're going to be solving for? And I would submit to you that since it's an unknown metal and we can know that metal, we can identify it based upon a comparison to a physical property, I would submit to you that we are going to be solving for the heat capacity of that metal in order that we can then compare it to a table of heat capacities. So that is going to be our benchmark. That's what we're going to be looking for here. And indeed, we will be able to put all this together. Notice that I said before, if we subtract an initial and a final temperature, we get the delta T. That is what this is. So there's a little work we would have to do ahead of time in order to plunk into this Q equals mc delta T the actual numbers here. So Q is 42.7 joules, which is what we had before. 32.5 grams, as that's given in the question. Heat capacity, well, that is what we're solving for in red. 3.4 degrees Celsius, well, we subtracted those two temperature values to give us what we want. So really, ultimately what we're just going to do is we're going to solve for the heat capacity. And what comes out of here now is 0.385 joules per gram per degree Celsius. That's what comes out of our calculator. And we would then go to a table of heat capacities, and we would find that 0.385 corresponds most closely to copper, so that the identity of the metal would indeed be copper. So in the last two examples, if you'll recall, I asked you to suspend disbelief because within the word problems themselves, there were amounts of heat that were dialed into the into a sample. Q, joules, those are immeasurable. We can't actually do that. So how do we apply heat capacity and actual heats, these joules, heat flow in an actual laboratory situation where we can't directly measure them? We find that if we need, in a laboratory situation, we need to find the amount of heat flowed, we can think about a system in which, imagine a system, if we have a sample of something, that sample sits in a surroundings, and any heat flow into or out of that sample will flow either into or come from the surroundings. With respect to my sample and my surroundings, that heat flow is exactly the same. Exactly the same. It's got a different sign, positive or negative on it, but the number is exactly the same. And that type of thing is what we use when we need to determine heat flow within a laboratory situation. This is known as calorimetry. The definition of calorimetry is the measurement of heat transfer from one body to another. Well, how do we do that if we can't measure heat directly? Well, let me set this up for you. In a calorimetry experiment, we carry this out in what is a calorimeter. A calorimeter is essentially a reaction vessel from which all energy is contained within. No energy from outside and the surroundings can go into the system, or the system cannot send any energy, heat energy most of the time, outside of that system into the surroundings. So we need an insulated system. That insulated system almost always, if you're cheap like I am, involves two nested styrofoam coffee cups. So you can use on a budget. This is a very, very good system because styrofoam is such a very good insulator that it stops any heat flow from within a system to outside of a system. Now, within these nested styrofoam cups, we have water. That is part of the system, and we put into that water a heated, if you will, metal sample. Or it doesn't have to be metal, but we're going to be talking about samples being of a metal. That heated metal sample, the heat will flow into the water, which is inside the calorimeter. It will be picked up by it. We find that any heat, as these arrows coming out of this heated metal sample are going into the water, which is considered the surroundings. If we have this calorimeter, which does not allow any escape of heat, any heat into the system, we find that the heat of the sample that is released equals the heat picked up by the calorimeter. Those Q's must be equal. They must be equal. We don't know what they are because they are not directly measurable, but they are equal. Now, Q of the sample, let's look at this. The heat of the sample, remember, Q equals mc delta T. So while I can't measure Q of my metal sample, I certainly can measure its mass. I certainly can look up a heat capacity of that metal, and I certainly can measure through various calculations the temperature change of that metal going into from the beginning of the experiment to the end of it. Similarly, heat of the water in the calorimeter. So really, Q of the calorimeter is the water within it. Now I can measure the mass of that water. I know the heat capacity of water, and I can measure the change in temperature of that water in this system. So let's see how this is done. If I substitute in, if we look at our, let me just clean this up a little bit here. If we look at our immeasurable comparison right here, these Q's do not help us much, but we know that they're equal. So what can I do? Well, since Q equals mc delta T, I can add in or substitute in for each Q in this case, the Q of the metal sample, just like we did before. Mass of the metal, heat capacity of the metal, change in temperature of the metal equals the Q heat of the heat flow into the calorimeter, the mass of water, heat capacity of water, change in temperature of the water. These are all readily available to look up, to measure directly, to calculate, and so on. So while this is, I would say this is an algebraic, ends up in being an algebraic equation with 6 variables. Ultimately, you're going to be asked to solve for one of them. Which one? That's where the design of the problem is worked out, knowing that whatever one we're tasked with figuring out, that would mean that all the other 5 of that 6 are readily available. Let's look at an example of this to see how we would approach this sort of problem. Okay, looks like a lot of information here. Let's get started. A sample of aluminum. So we know that we know what our metal sample is heated to 39.4 degrees Celsius, and it's then placed in a calorimeter containing 50 grams of water, and that water is initially at 21 degrees Celsius. The temperature of the aluminum water mixture rises to 23 degrees Celsius. That means that at the end of the time, both the aluminum and the water, after all heat flow has stopped, are at 23 degrees Celsius. What was the original mass of the aluminum? So how do I know this is a calorimetry type problem? Well, we'll have some visual cues there. It says calorimeter. Anything you can bet that anything problem that has the term calorimeter or calorimetry or anything like that in there, oh, we're going to use this is a calorimetry problem. The heat Q lost from the metal is the heat Q equal to picked up by the water. So we're going to set this up in the fashion that we see here, like we saw on the previous page, where we substitute Q for MC delta T of the metal with MC delta T of the water. And looking back over that problem, we would find that which of these 6 variables is the unknown that I'm going to be looking for. Well, again, let's look. What was the original mass of that aluminum metal? There it is. So the mass of the metal is what we're going to be solving for. That means all 5 of these others are readily calculable, look-upable, or if that's a word or a term, but they are available to us. So if we're solving for the mass of the metal, we can rearrange the rest of these terms such that it puts the mass of the metal all by itself algebraically on one side of the equation. Once we do this, we have a lot of other terms to plug in. And I would like to point out that notice certain things are given, but certain things have to be calculated from the problem. For instance, the change in temperature of the water. Well, that goes from 21 degrees Celsius to 23 degrees Celsius. That's 2 degrees Celsius. Fair enough. The change in temperature of the metal. Well, the change in temperature of the metal goes from 39.4 degrees Celsius to 23 degrees Celsius. And again, we would do a subtraction to find those terms. The heat capacity of water is very easily looked up. The heat capacity of the metal, which we know is aluminum, is very easy to look up. And the mass of the water is given in the problem itself. So really, this just involves putting a bunch of numbers in there for that, and we just calculate through, and we come up with 28.3 grams. Now understand that a possible question, calorimetry type question of this sort, could really solve for, ask you to solve for any one of these 6. Well, we looked at one example here where we were solving for mass of the metal, but I could just as easily look for one for calculating the heat capacity of the metal and identifying it, or the change in temperature of the metal, or change in temperature of the water. All of these would be achievable algebraically, because knowing that If you know which one you're looking for, understand that in any of my problems, the rest of the or calorimetry problems, the rest of them will be either given to you directly or calculable.